10, we looked at parallelizing compilers, and essentially we saw that for them to be able to guarantee that parallelization is valid, the loops have to be so-called perfect loop nests. There are many loops which are not perfect loop nests, but which have no data dependence at runtime that would prevent the parallelization, but the compiler cannot see it. Okay. Other loops, they have sometimes data races if the iterations are run in parallel. And if that sometimes is but sufficiently infrequent, then it may be suitable to run the code in parallel anyway and detect by library codes which log what is happening. I mean, what each iteration is, which data they access, and if there is a conflict, then this speculated parallelization is restarted. And well, what will happen then? For instance, the loop can be run sequentially. Okay, it's not so easy to make this efficient, since software must check during runtime whether there are conflicts between the iterations. And such checking obviously takes time. Okay, but with hardware transactional memory, it appears to be obvious, one can imagine, that hardware transactional memory is ideal for speculative parallelization. Since the software overhead of detecting conflicts can be done in hardware instead, which is much faster. Okay, and this study in a very prestigious journal, IEEE Transactions on Parallel and Distributed Computing, by 3 researchers from Brazil. They have not modified a parallelizing compiler, but they have instrumented certain benchmarks and see, I mean, in a way that the compiler would have been able to do, and measured the performance improvement in this way. Okay, that is how research can and should be done, because doing this manually, it will evaluate how a perfect compiler would be able to do it. If they would instead spend 4 years modifying a parallelizing compiler, maybe it doesn't take 4 years, but it's certain to take more time than expected. And then the result would not be as interesting, since we want to know the upper bound, how well can this be done, and not for a particular implementation. Okay, so then it's better to do it like in this way. In other studies, it's more important to see how a certain algorithm actually can do that, or a certain implementation. But to evaluate how well we can do speculative parallelization using hardware transactional memory, it's better to do this by hand. Okay, so which benchmarks were used? It's a benchmark suite called CPU 2006 or Spec CPU 2006. Spec, it's an industry consortium for evaluating the performance of CPUs and compilers. And this is it was created in 1980s, and the first version of this benchmark suite was from 1989. And this was a reaction to silly benchmarks that were abused to create good performance numbers, but which mattered very little to the real world. Okay, so all the computer industry is, CPU, computer manufacturers, they are using these benchmarks, and that's very nice. Okay, so the current version is from 2017. Okay, so what did they see? Well, I should mention also, these benchmarks are very difficult to parallelize automatically, because they are written in well, we can see that they are written in C, C++, and Fortran. And at least the C programs in this benchmark suite, which I have used quite a lot, I don't compile neither C++ or Fortran. Well, in case you wonder, I have been working on optimizing C compiler for quite some time, and they are very difficult to parallelize automatically, these programs, due to pointers, for instance. Okay, so using 4 CPUs, although the cores, 4 cores, although Power 8, for instance, has more than that, they could see speed-ups of up to 3.8. And this is really promising. We cannot expect to get 4 times speed up. That's normally unrealistic. But this is very good. And recall from the lecture on transactional memory, there are several different things that can make it, which introduce some overhead. And so with this approach, we can get really good performance on old sequential code. Well, this is just one representative benchmark suite of what many workstations are used for. But it's not for every program. There is no such thing as a typical program. But for many relevant programs, we can get really good speed up without having to manually parallelize the code. So this is something to look for. Okay.